So we can start with the second talk of this afternoon. So our second speaker is Alexander Avanov from the Simon Center, and he will tell us about anomalous helicity non-conservation in Euler fluids.
Thank you, Francesca. First of all, let me thank organizers for inviting me here. It's nice to travel after a long break, and it's nice to I'm going to talk about classical theory with anomaly, and that theory turns out to be Euler barotropic hydrodynamics. So what I'm going to do is first I'm going to introduce the barotropic hydrodynamics, and this is well-known stuff, but I will put basic equations here, and I will remind you that there is a very peculiar current which is conserved in that theory, and this is called Helicity Conservation. And then we had this is work in progress with Paul Wigman, by the way, and we observed that when you include background electromagnetic field, then this current stops conserving. And the divergence of the current is equal to familiar expression to E times B. Okay, so first I will just derive it in a very engineering way. I will just take equation, differentiate, and show, well, not in detail, but then we will consider more geometric derivation of that equation. It turns out that it's very geometric. And then I will think about symmetries which lead to this anomaly and compare with famous ABJ, Adler, Bell, Jakiv, or Carroll anomaly. And the story is in 3+1. Okay, and please interrupt me with any questions because people have different backgrounds. So first, let me start with barotropic fluid dynamics. And I will start with the system of hydrodynamic equations, and one of those equations is the continuity equation. And another equation is so-called Euler equation. And there are many ways to write it. Let me write it in the most conventional way first. So this is Euler equation, which is basically tells you that the acceleration equals to the force divided by mass. Okay, and I will also add external force, which is due to electric field and magnetic field. Okay, so here there is this row I will treat as a particle density. The mass is absorbed into the pressure, P is the pressure, and electric charge divided by mass is absorbed into electric and magnetic field. I may say a few words about units later, but this is like basic form of the equations. And the pressure is generally a function of density, temperature, and other thermodynamic quantities. And this is equation of state for that system. But in this particular case, we will neglect temperature dependence and dependence on other quantities, and then it's called barotropic. Okay. So this is equivalent to saying that it's barotropic. It can be some particular matter which has this relation, or it can be that for given flow, we can neglect dependence on other quantities. It doesn't matter. So this equation is a basic stuff that I need. Okay. So any questions so far? So, so these are four equations. There is one continuity equation, which is conservation of mass. This is essentially together with this conservation of momentum. These are three equations, and I have three unknown functions, which is density and three components of velocity. So I can, in principle, solve it and putting some boundary conditions, solve any Cauchy problem, in principle, of course. Of course, turbulence is one of those problems, so it's not always possible. So one interesting way of rewriting this equation is the following, and it's very suggestive. Well, maybe not. So let me write the following equation. One more comment before I go further. So this is not magnetohydrodynamics, okay? I'm considering the charged fluid in the presence of external fields, and I do not consider the feedback of the currents and charges here on those fields. So I'm not using the second pair of Maxwell equations. I use the fact that E can be written in terms of scale and vector potential, and B as well. That is the first pair of Maxwell equations, but I do not ever use the second one, and that's really important. Because usually, okay, let me first tell the result, and then I make my comment about our surprise. Okay, so this is equation which is identical to this equation. You can see how it works. If you differentiate vector potential here, bring it to this side and combine it with gradient of scalar potential, that's electric field. If you now take this V cross B, put it in the right-hand side, this is V cross B. And the only thing unknown here is this one, but I'm basically writing that dP equals rho d mu, and mu here is chemical potential, and this is thermodynamic relationship. So if this is function of density only, then you can always find the function of density, which is mu here. So you basically can absorb this 1 over rho under the gradient, and that's the property of barotropic dynamics which I need.
And so what is omega?
Say it again. And oh yeah, one more notation is omega is a standard notation for vorticity, which is curl of velocity. So if there is a rotational part of the flow, that brings non-zero omega here. Okay, and now let me take a curl of this equation, and I obtain the following equation: dt omega plus b. And then let me write first in original form. As I said, this is very important property of barotropic dynamics because this is complete gradient. So when I take a curl, it disappears. So this equation written on vorticity plus magnetic field already does not know anything about peculiarities of the matter. It's all parts specific to matter disappeared. Okay, this is a standard trick, and the way to say this, that this equation, if you think about it, is a way to say that omega plus b is a field which is frozen into flow. So it's basically transported. Because it's not a scalar, it's transported in more complicated way, but basically you can say that Lie derivative of omega plus b is 0. So, any questions? Okay. Now, there is one more important, well, many more, but there is one more important for me quantity, which is called helicity, or fluid helicity, or kinematic helicity. Again, there are many names. And this is defined as integral of velocity times omega over volume. Okay. And it turns out that if there are no magnetic fields, electric fields, then the well-known result is that this quantity is conserved. It appears as a miracle that it conserved because you basically take this equation, this equation, using this and this, you can easily do this exercise, and you obtain that it's conserved. Okay, but there is some geometry behind it, and I will try to explain it. This quantity conserves like a charge, but I can write also local expression, and local expression will look like this. Where the axial density here is helicity, and the axial current here has a particular form, as it has a very standard term like this. So the helicity density is transported, but there is also additional term, which is this. Okay. But the important thing is that it's locally, the density of this quantity, namely this object, is locally conserved. And as I said, it's not clear, is it coming from any symmetry? So far, it looks like a kinematic identity. You already use given equations and derive that. And at the end of the talk, I will explain the symmetry origin of this. And for now, we'll just consider this as given. Okay, and now we turn on electric and magnetic fields, and this will be the longest formula, but I have to write them down. So now I will go to the second part, which is H in electromagnetic field. So the reason I'm writing these equations, I need only one of those eventually, but because I haven't seen them, and that's a surprise. Because this seems like a very basic model, and there are a lot of similar equations in magnetohydrodynamics, but it's a little bit different. And okay. Okay. So this is the evolution of helicity density in the presence of electric and magnetic field, and it is not conserved because of this term. Okay, so if this is the derivative of densities, this is the divergence of the flux, but there is term which cannot be absorbed into the divergence. And additionally, one can consider the following equation, which is called mixed helicity. It's magnetic mixed with kinetic helicity. So it's mixed helicity, and it has very similar type of equation. So I'm not writing vector indices here, but I hope it's clear from this. So that this is vector, this is scalar product, etc. If not, please let me know. I'll write them. And then there is a similar term as well, but with different coefficient. And then we already see the main feature that in the right-hand side, E dot B appeared. Okay, and this is not conserved as well, as you can see, because there is this term plus this term in addition. So, there is a very interesting limit, namely when this term is zero, when there is a force-free motion, when there is some motion where there is already no force, then you can see that in this case, kinetic helicity and mixed helicity are conserved separately, right? Well, yes, because if this is zero, then E dot B is also zero automatically. And therefore, this is right-hand side is zero, so both conserved separately. And this is well known in magnetohydrodynamics, because in magnetohydrodynamics, they study the back action of the flows on field, and they also add usually some additional constitutive relation. And the typical one they add is that the current equal conductivity multiplied by E plus V cross B. Okay. So this is the density of current, and this is Ohm's law, right? But with a force which includes also electric force, not just electric force. And then if you say that in the limit of ideal, it's called ideal MHD limit when sigma goes to infinity, then this is ideally conducting liquid. Then obviously that for any finite current, you divide by sigma and you see this zero. And so it is known that in ideal magnetohydrodynamic limit, helicity, kinetic helicity, and mixed helicity are conserved separately. Okay, any questions? Okay, now I'm doing something really obvious. I'm saying that, okay, look, they're almost conserved except for these basic terms. So let me multiply this by 2 and add it to this. And this is what I obtain. I obtain dt v omega plus 2b, some very weird combination. And then plus gradient, divergence, sorry, v plus 2b times v, v multiplied by omega plus 2b times v. So this is the same quantity multiplied by velocity plus omega plus 2b multiplied by this interesting object. Okay. Then this piece, because it's multiplied by 2 or by 1, so this has minus v cross e plus v cross b. And this is equals to EB. Okay. So this combined quantity practically almost conserves, except for E and B have parallel components. Then it is not. But then it reminds a lot the equation for axial anomaly. Okay, and this is the main subject of my talk. Any questions? So far it's just algebra. You can do it from Euler equations. We asked a lot of experts. We did not find it in literature. Probably it exists somewhere. I don't believe that this thing, starting from that fundamental point, is not somewhere. Okay, so you can read from here, this is the axial density, and this is the axial current, this quantity. And if you're familiar a little bit or saw relativistic hydrodynamics in presence of anomalies, then you can actually recognize something here very interesting. This term usually is called chiral vortical effect, and this term is usually called chiral magnetic effect. So the current has a constitutive relation which tells you that there is a part of current proportional to vorticity and another is proportional to the magnetic field. So these kind of formulas were obtained in relativistic limits, but they're not quite the same. So I'm not going to talk about relativistic stuff today. Okay, any questions? Okay, if not, I can definitely raise this.
Maybe I can ask a question going back to this Blackboard. Sorry,
to this?
yeah, no, about the barotropic. So
yes.
This barotropic case. So the fact that the state equation does not depend on t. So I mean, is it a restriction on the type of matter that you can discuss, or just corresponds to say that the temperature is fixed? And
yeah. No, I mentioned this. It's probably if you talk about real matters, there is always dependent on temperature or anything. It's just the question whether for given flow you can neglect it or not. Very often, like here outside, when you have an airflow, you can treat temperature as almost constant for most of the cases, right? So this is like good example of barotropic flow. Well, there are other things there out there like viscosity and stuff like that. This is all for ideal case, of course, but because if there is a viscosity, then all these things starts also diffuse in addition to being conserved. But in any case, it's not really big restrictions. There are a lot of barotropic flows which can be approximated as barotropic flows. So this is not really, I don't want to think about matter which doesn't have temperature at all, because usually in that case, this hydrodynamics is not applicable too much, but mostly when it's just not important. Okay, so the next story, this looks very puzzling. This is just algebra, and somehow we get this equation, which looks nice. So I will describe some geometric picture. Actually, the Euler equation, the inviscid ideal equation, is very geometric in spirit. So what I'm going to do is I'm going to do the following. and of course I erased the only equation which I needed. Oh, okay, but let me rewrite it. It's okay. It's quick. So let me take this equation. This is original Euler equation, as you remember, rewritten in a form to include external fields, just as a shift of the velocity and vorticity and chemical. Okay, equal sign somewhere. Okay, so this is the original Euler equation, and I'm going to introduce more notations. It turns out somehow that four-dimensional notations are extremely useful here. So although this is purely three-dimensional, this is non-relativistic. You can see v squared over 2. This is actually particularly Galilean invariant even. But many things I'm going to talk about do not depend on details. And four-dimensional notations are very useful. So let me introduce notation pi 0 equals minus mu minus v squared over 2 plus a0. And pi I equals vi plus ai. Now I stress that this is spatial components only, and this is new notation. This is essentially velocity with vector potential, this one, but this is new notation. And I will also introduce J0 equals rho and Ji equals rho Vi. So this quantity is like a canonical momentum per particle. So like remember this pi minus a is velocity. That's what our usual classical mechanics tells us. And this is current, the one that is conserved. So for example, in these notations, I immediately write d mu j mu equals 0 instead of continuity equation with explicit time derivative. Okay. Okay, and more importantly, with these notations, I can rewrite this equation in the following way. Let me first write it, and then I'll roughly show you how it goes. So this is equivalent to this. Okay. You can roughly see how it goes. This is dt pi I, right? This is di pi 0, which you go back, you get one of the components of these combinations multiplied by 1. So let me multiply this equation by density. Then it's multiplied by zeroth component of the current, which is density. And then this piece by this famous vector identity, you just write this way for spatial components. Okay. So this is actually form of that Euler equation. You see that it's very geometric already here. In fact, it can be written as that Lie derivative of d pi is 0. Oh, sorry. No. Yeah, that's right. So Lie derivative of d pi is 0. Actually, I have to be more careful. This is not written to this, but from here it follows than this. I can go into details later. So you can derive from this immediately this equation, which tells you that combination d pi, which is roughly the space component is vorticity plus magnetic field, is transported by the flow. We already saw it by taking the curl of this equation, but this is like a very, very geometric way. And these are all four-dimensional formulas. Okay. Okay, then we can do more. So let me do it in indices, and then I will say how it looks even more geometrically. So I'll take this equation, and I will use the following identity. And so this, sorry for this boring piece. This identity helps a lot. Okay. So this is a little bit cryptic, but this is actually identity for any fields. The derivation of this is the following. If you take this delta function, epsilon, and multiply it by this, and you anti-symmetrize over all 5 indices here, then this is 0, because we're in 4 dimensions. So 2 of the indices will repeat. And now if you take this and expand, it turns out that it collects into this identity. Okay? There are smarter ways of doing this. I will say in a second. So, but what's important from here is that if I multiply now this by j alpha, j beta, both sides, right? These are 3 indices here, alpha and beta. So I contract it with my current, and j beta multiplied by d beta pi is 0. Okay, so the left-hand side is 0. And the right-hand side produces here j squared, j mu, well, j alpha. And the current squared is never 0. It has density in it and so on and so forth, which means that d pi is 0. Or if you want, this thing is 0. So my claim is that this is essentially Helicity conservation, and derived in a more geometric way through the transport by the vector field J. And the way to see it is just to write d mu epsilon mu nu lambda rho pi nu d lambda pi rho equals 0, which is just component way of doing that. Now look at this expression, look at its zeros component. Okay, its zeros component is epsilon I j k I d lambda pi I d j pi k, and this is nothing else but helicity. The pi, in the absence of vector field, this is velocity, so this is velocity times vorticity. So the zeros component of this current is axial charge. Yes.
So yeah, when you put the background field, then pi is not gauge invariant.
Right.
No?
Now I'm going to this.
Okay.
So what I'm saying is that this modified conservation of helicity. Without vector field, it is just conservation of helicity. And now we will see how to derive modified one. Yeah, that's a good observation. So, and I specifically, let me write this in a differential form expression because it will be just easier to manipulate. So I'm saying that this current, which is 3 form, but you can also make vector out of it, is conserved. We just proven it, okay, from Euler equation. But there is a problem with this current. It's not gauge invariant, right? Because pi, as you remember, is velocity plus a, and velocity is gauge invariant object, but a is not. So I have this familiar thing in anomalies that you have conserved current, but the density of current is not gauge invariant. So what we are going to do is we are going just to rewrite it as v plus a dv plus a equals 0. And let me do this computation quickly because it's very simple. It's v dv term plus a dv plus v dA plus a dA. Okay, just, and this a dv I don't like because it's not gauge invariant. So I write it as minus d of av plus vda instead of this. Okay, this is under derivative, so this is curl-free term. When d acts on it, it kills it. So I remove that, and I have d of v. This term I combine with this two, v times dv plus 2a. Okay, and there is also one more gauge non-invariant term, but when I take d of it, you'll get dA, which I put in the right-hand side. Okay. So what we achieved is that we have the conservation of helicity current, but not quite conservation, anomalous non-conservation. But non-conservation is only due to the background field. Okay, that's the result. And again, you can easily see that the zeros component of this current is velocity multiplied by vorticity multiplied by +2 magnetic field, which is our axial charge density. And it's more difficult to check that actually its spatial component is given by this expression. The reason it's more difficult to check, because the reason this formula is so compact is nice, is because there are some time derivatives here. So, and you have to use again equation to substitute those time derivatives, etc., etc. But at least you know that the axial charge is conserved, well, up to this non-conservation, right? So you to get expression for current density, you have to do some additional work, but nevertheless, it's not so difficult. Okay. Oh, I'm practical on time. Okay. Any questions so far? Because now okay, we already see some similarities with axial anomaly story. Now what I want to do is I want to clarify the role of symmetries in all that, and just make even closer parallel to the axial anomaly.
Maybe a question. So maybe you already said
Yeah.
it, but so the fact that the equations organize in a relativistic covariant way, is it because this is the non-relativistic limit of a equivalent relativistic story?
You can probably say so, but in the next part, I will show you the action for this hydrodynamics, and you will see explicitly that I can actually separate interesting story I'm talking about from relativistic invariance. So I basically will put relativistically invariant or non-invariant term describing the symmetry of space-time and everything as one part of action which does not play any role. And only symplectic part of the action will play a role, and that is manifestly invariant. I'll explain. I'm not sure that I understand this that deeply, but getting this from non-relativistic limit of some relativistic theory is an interesting question. You can do that, but it's a little bit tricky. It was considered this kind of limits in literature. You have to take some special background gauge field to make sure that the currents are finite in that limit. But in principle, possible. Yeah. So there are some relativistic analogs of this. But for me, the most remarkable part here is that this is about just water. Well, a bit charged, but this is really has nothing to do with Dirac C field. So it probably has something to do, but it means that finite density of water somehow simulates this Dirac C of massless Dirac sphere. Okay, so this is quite remarkable, I think. Okay, so let me, because I have time, I think, so let me give a quick digression in one very simple example, just to show what I'm after. So what I'm looking for in terms of analogies. So let me consider the action of 1 + 1 boson. Not even compact. I don't need even compactness at this point. So it's the simplest possible theory, which obviously has invariance phi goes to phi plus constant. And there is a conserved current J mu, which is basically d mu phi. So and it conserves on equations of motion. Sorry for telling so trivial things, but it will be important for me. There is additional current, which is conserved. Well, additional probably is exaggeration, but this is we can define current like this. This is epsilon mu nu, Levi-Civita symbol, and obviously it is conserved. So d mu j mu a equals 0. And in this formulation, it's not conserving because of any symmetry, right? It's just because, well, there is some essential symmetry telling me that somehow this phi essentially relatively smooth. So the derivatives commute. But if derivatives commute, you don't need anything else. You just get this as a topological property. Okay? So, but now the question is, what happens with this equation if I gauge this? And I'm pretty sure you all know this story, but let me just, I want to make real parallel with what I'm about to do. So I will put gauge field here. So I assume here that A goes to A plus d lambda, and phi goes to phi plus lambda. So phi is like superfluid phase. Okay. And let me call now this J tilde. And there is no doubt it's still conserved, right? Commutative of derivatives is commutative derivatives. But we have a problem because this is not gauge invariant anymore. Okay. So let me fix it. Let me write that G mu A is epsilon mu nu d nu phi minus A nu. This is gauge invariant. Let me see what this is. And I have to differentiate with respect to mu, and I have minus f. Okay, epsilon mu nu, okay, f star. Okay. So, yeah. Oh, yeah, that's right. Thank you. The other current I can fix. So I can fix the other current, no problem, it's conserved. Yeah, that's good. Otherwise, it doesn't make sense to talk about. So I have two conserved currents, one apparently for symmetry reason, another topologically. I gauge the one for symmetry reason, and I get the one which was topologically is deficient. It's not gauge invariant. I have to correct it, and then I see that it's not conserved, it has anomaly. That's a story in 2 words. Okay, that's the simplest example of this 't Hooft anomaly. It's conflict between these two global symmetries. So what I'm going to do is I'm going to find a similar thing in my example of hydrodynamics. Okay, and now we go back to my item number 4, which is analogous with this and more complicated 3+1 dimensional examples as well. Okay. So let me skip this. So let me again write my equation d mu j mu. Well, yeah, j mu equals 0, d mu j mu xl, I will call it, equals 2 e dot b, and j mu is rho v. These are 4-dimensional notations, and ja mu is v. Well, let me write it in a formal language, omega plus 2b. Okay. So we understand what's going on with this one. This is the charge symmetry. It's not really that much clear because original equations for Euler equations which I wrote were absolutely gauge invariant to start with, right? They only contained E and B. But I already rewrote them in terms of pi so that you know that how it acts. This pi contains A, and A we know how to transform, etc., etc. So this we sort of understand. This one we don't understand at all because so far it appeared as a miracle. The question can identify some symmetry which is responsible for cancellation of helicity, for conservation of helicity. Okay, essentially find some symmetry, use Noether theorem, and find this conservation law for this quantity. Okay, and when you talk about Noether theorem, you usually want to start with some action. Consider the action on the fields which is symmetry, which does not change the action, and then derive that. So action for hydrodynamics was notoriously difficult subject, and is still not very much known. And the reason is that Hamiltonian actually is much simpler. You can the Poisson brackets well, actually, quantum commutators were derived by Landau in 40s when he thought about superfluid helium. And then people took classical limit through Poisson brackets. This was how it was first derived. But essentially, you start with the Hamiltonian. Let me use this part. You start with the Hamiltonian, which is very simple, which is kinetic energy of the fluid and internal energy of the fluid as a function of density. And from here, you can make pressure, which I used so far, and chemical potential. So you start with this Hamiltonian, but you ask what's the Poisson brackets which generate Euler continuity equations. And then there is a list of Poisson brackets. You know how to commute, what's the Poisson bracket of rho with velocity components and two velocity components as well. Then this one is relatively non-trivial. It has vorticity on the right-hand side. But they're known, and if you just apply this commute Hamiltonian with density using and density commute. Commute with density, you get continuity equation. You commute with velocity, you get Euler equation. But then you ask, what about helicity? And indeed, you can take integral of v dv and commute it with Hamiltonian using this Poisson brackets, and you'll get 0, which means that it's conserved. The problem is that this object is so-called Casimir. So it actually commutes with everything. It commutes with density and with velocity separately. So this object, you cannot commute it with any observable like density and velocity and get 0. So therefore, of course, it's conserved. It's commutes with Hamiltonian. Okay. But then you start with this and you want to write action. But there is a Casimir, which means that there is a 0 mode in this Poisson bracket. And when you go to symplectic form PQ dot necessary to write the action, you have to invert Poisson brackets, and you cannot do it right away. And there are many ways of doing this. And the particularly useful for me way is that you can expand your phase space. You consider not only rho v, but some other auxiliary fields. Then you write action and make sure that these equations produced by the action produce Euler equations for rho and v. Okay. So, and actually, this action is very nicely can be written very nicely in pseudo-relativistic way. So let me write the following action. This has a long story, all I just said, but I will just try to, well, not even convince you, but ask you to believe me that this works. Okay, so this is the action. The action is a variational principle, which should be considered as a functional of the following fields. Theta, alpha A, beta A. And here, pi mu, and this is very important, is just a notation for the following combination of fields. Okay. So instead of velocity and density, I have current, which will be identical to rho v current, which I will use later. But instead of, and my additional fields include this theta, alpha, beta, and alpha, beta comes in many pairs. So A here is from 1 to 1, 2, and more. It's for me important that it's 2 and more, but it doesn't matter. And pi mu is just a notation for the following combination of these fields. Okay. So then what you do is the following. You take this action and vary over j, over theta, over alpha, over beta, and you write all these equations. And then you use some combinations of them and write equations for those combinations, and they become Euler equations. And the main question is, I should comment on this one. This one is some function, some density which depends on fields. In my case, which I started from, it's rho v squared over 2 plus epsilon of rho, just energy, the fluid. Here notations are as before, the ji is rho vi and j0 is rho. Okay. So, but this will play absolutely no role. So you can put here a relativistically invariant combination j mu down or any function, and it will produce a relativistic hydrodynamic equations. And I will be playing only with this part from now on. Okay. Okay. I hope you believe me that this can produce equations further. Well, one comment is that J actually can be integrated out. Then you will have derivative of this, and this will give you connection between pi and J. So it will express your velocity in terms of the potential. And then it's called Clebsch parametrization. Clebsch parameters. So this way to expand the phase space was basically invented by Clebsch. Okay. And now let me look at the part, or at this part, which is central part for me of the action. It's J mu. Let me write it explicitly: d mu theta minus a mu plus alpha a d mu beta a. Look at this expression. You obviously see that there is a symmetry. Theta goes to theta plus constant. This is my standard U1 charge symmetry in this case. Remember that in Euler equation, it was not clear. There was rho and velocity, and they did not transform at all. They were neutral objects. But this one transforms. And moreover, it's gauged here, right? So this is gauged by field A. That's one comment. And secondly, finally, the last part is that I have to find the symmetry of this action, which produce conservation of helicity. That's the most technical part. It's actually known. Okay, that one is useless. Okay. Okay. That's right. It's actually good. I don't have to raise that because we have to compare with what I'll get now, right? I promise that. So now we'll talk about what is known as relabeling symmetries. So the question is, when I will do this procedure, what guarantees me that the equation for velocity and density, defined in terms of theta, alpha, beta, they will flow in such a way that they will still be always equations of velocity and density, and there will be no alpha, beta, theta equations explicitly, only in the combination of this. And the idea is the following, that there are many, this is very excessive parameterization of just three-component velocity, and there are many transformations here which do not just change this combination. Let me give you just one simple example. Take one of the alphas, or all of them, and shift it to alpha plus any function of beta, okay? So this will add f prime of beta. You can write it as d mu of f, and you combine it with this, and if you change theta to theta minus f of beta, these combinations will remain invariant, okay? So it means that this combination, this is like really exact symmetry. So if you have this symmetry, it will be preserved. So it basically does not allow you to go outside of your combination pi. You cannot just write pi equals alpha dot because that symmetry will not be preserved. Okay, this is a basic idea, but actually there are quite a lot of those symmetries. Because essentially you can do this theta, alpha, beta, and do with them anything you want if you try not to change pi. Okay, and this is actually S-diff group. And physical meaning of this is that there are two formulations of hydrodynamics, Lagrange and Euler. Well, there are more, but these are two main ones. And Lagrange started by just saying that there are fluid particles and just write equations for fluid particles moving. And Euler said that let's consider the field of density and velocity. Lagrange has more degrees of freedom than Euler. So Euler is a reduction of Lagrange. So you put only consider only particular combinations. But no matter how you call fluid particles in Lagrange, you can relabel them. This will not change anything. No Euler dynamics will be changed. And these alpha, betas, and thetas are actually labels of those particles. That's the origin of the name relabeling symmetry. and the physical idea behind that. So, but I don't need the whole thing. It's like SDIF, it's huge group. I need just one particular subgroup, which is responsible for conservation of helicity. And let me write explicit formula for this one, and that will be the end of the talk. Yeah. So let me write this. I have some constant parameter eta, and I do write this. The relabeling symmetry was studied a lot. Usually people study this in Hamiltonian formalism. I did not see this derivation exactly like this, but also probably exists. So the same for beta, essentially. And a little bit different for theta. Okay, and delta J is not transformed. So this is why this part for me is not important, because it's just identically, it's trivial. Okay, so let's consider this particular transformation. The physical meaning of this is relatively simple. This is the change of alpha is eta times derivative of alpha will be just change of argument of alpha by eta. It's translation. But this one shows you in which direction, and this is vorticity divided by density. So this is the translation of my alpha beta parameters in the direction of vorticity with the magnitude vorticity divided by density. This is a particular, you can kind of see that this is sort of like something to do with helicity, right? There's a vorticity, and if you move along the vorticity, you get helicity. So this is what is, and this is explicitly entered here, right? So this is the change. And essentially, which one? J, you mean this one?
No, pi is the first in terms of theta and alpha, and then you use pi to change theta and alpha.
No, I is, you mean this I? Pi. Yeah, that's right. So I'm allowed, like even here, I changed alpha by function of beta, right? Here I change alpha by function of gradients of alpha, beta, theta. And I have a right to do that, right? You can do transformations like, I know, delta x equals x. Not really a problem, right? So this is not a problem. Let's see. Yes, it is. Yeah, this is next line. Let me do it. So one can check. Yeah. So this is not transformed. But let's just formally do this. Let's just take this formula and apply this infinitesimal change of variables in my action. And you can see that it's already almost everything is dead here, right? Because there is ji pi I here, it's gone. This is not transformed. A is not transformed. So there is only pi 0 left. Let's look at pi 0. Delta of J0 pi 0. J0 is raw, so it will cancel this raw essentially. That's why I need it. But other than that, it's just given. Where is it? It's just eta epsilon mu nu lambda rho d mu pi nu d lambda pi rho. Again, some computation is necessary, but you basically get this. So this piece changes by this. And this is full derivative. So the action, the Lagrangian is changed by full derivative. So it's perfect symmetry. And this is actually conserved quantity associated with that. I mean, you can, again, substitute, say that eta is a function of x and t, differentiate, and you get conservation, which is exactly this, which is d pi d pi equals 0. So what I showed is that there is a particular part of relabeling symmetry group, which is the symmetry of the action, and which results in the conservation originally helicity, and now anomalous non-conservation this modified helicity. Because equation d pi is the same in both cases. But in the second case, when gauge field is present, I say that this is bad, and I do that exercise which I already did, and it results in anomalous non-conservation. Okay, so basically that's it. Let me just quickly say that we derived formulas for generation of helicity by parallel electric and magnetic fields. I'm still looking for these formulas in literature. If you know something, let me know. It's just surprising that I cannot find it. And we showed that it can be interpreted at Hooft anomaly. Unfortunately, only very it's not the full story yet. It's being developed. What I showed here is that as soon as you introduce the gauge field for the charge symmetry, then the relabeling, the conserved quantity associated with relabeling symmetry is not conserved anymore. So this is what we showed here. It would be nice to really find the exact representation of this as in electrodynamics, to find what's fermion and all that. So there should be something. And we have some partial progress, but I'm not ready to talk about it. And that's the story. One more comment on units. I claimed, I think, in abstract that I can show that it's the same as classic Dirac fermions, and you should stop me right there here because it's classical. And the coefficient in front of anomaly, although it's not written typically, but it has h bar in it, right? So let me explain what was meant. I will send you a copy. I'll just use this. Okay. The story is the following: that if you really, and nowadays you can, I have really difficulty to find somewhere where anomaly is written with coefficients. I mean, it's disaster. But typically, one of the formulas that you can find is something like this. I hope I'm not wrong. Okay. Sorry, 2 pi squared. And if you write FF here, even more common, then it will be 1/16. Okay, that's a coefficient many people remember. So what I can do is I can rewrite is that 2 multiplied by electric charge squared E times B. Okay. So this is, notice that this is not H bar, but H. Okay. And HC over E is known as magnetic flux quantum. So this is essentially if you express E and B in terms of magnetic flux quantum, you get 2EB. Okay. Well, it's what about us? So we have 2EB anyway, but what I want to say is that if you say that we want to measure velocity in units of the wave vector, and remember that velocity has meters per second, and wave vector is 1/meters, then I can introduce rescaling by some arbitrary thing, which is H Planck constant. So this is just my rescaling of velocity. And if you substitute it in those equations that I have, you will obtain exactly this. With this, and this 2 is exactly that 2 that I used all the time. Okay, what is this? So it looks like a cheating. It's somewhat cheating. So this H over M gamma is known as Onsager circulation quantum. So in quantum mechanics, in superfluid quantum mechanics, the circulations of velocity is quantized in units of H over M. So I'm basically saying something like that if in my fluid, although it's not superfluid, I started with just Euler equations, but if I think of this, that and split vorticity in the tiny quanta with circulation gamma each, and I modify and I simulate my flow with this splitting into many vortices, then if the flux quantum of those vortices is exactly the one which is in superfluid dynamics on Zager's ones, then I will get coefficient exactly like an ABJ anomaly. So this is sort of kind of ready for quantization. So I'm saying that all these coefficients anomaly, so far it's all classical story, but it's kind of prepared for quantization of the theory and ready to produce right H-bar dependent quantities. Okay, thank you. I'll stop here.
Okay, do we have more questions?
Could you write an inflow picture for this anomaly, and what would that mean?
Absolutely.
And what would that mean for the fluid? For the...
flow into. So okay, flow anomaly, inflow anomaly. This part I did not finish yet. Well, I have some other examples which are similar, but in principle, what you should do here is you should also gauge the other symmetries, this relabeling symmetry. And the first term is clear. You just write a pi d pi, right? So you just write this, and this is not gauge invariant, so you fix it, etc., etc. But this is only first term because this term itself is transformed under relabeling, and you have to be careful. If you know the story about Versumina-Witten term, then you can add J current multiplied by additional gauge field, but then you have to add high order terms because the current itself is not invariant and so on. You have to fix it. So this part I did not finish. It looks like there is some non-abelian symmetry in plane, but I'm not sure. I'll be happy to discuss technicalities. But okay. So if I gauge this, then there will be term. Something like a tilde ATA integral over M5, and which is supposed to be like inflow into that fluid. To answer what physical meaning of this, I have to first answer what's the physical meaning of this A tilde. One more comment, sorry for a long answer, but one more comment is that in this fluid, in this particular fluid, there is a lot of confusion because it's Gaussian invariant. So basically, things like spin connection comes together in a sum with gauge transformation. So it's really hard to separate this in this formulation. So you have to be careful. So what I think it means is that you put something like torsion in the A tilde field. Is you put something like torsion, so you steer your fluid with this field. But don't catch me on that. I'm not sure. And then if that's true, then this is basically like you have external way to manipulate this fluid. I mean, there is no fifth dimension, so well, at least we condensed matter theories don't quite believe that. So it just means that you somehow with some forces manipulate in a particular way the system. But maybe some internal motion is possible. I don't know. It's basically no physical interpretation.
Okay, thanks.
Mm-hmm. It's a good question.
We have more questions.
I think that the 1 + 1 dimensional example you gave, I can cook up an explanation in terms of things that I know, in the sense that, well, I think first of all that this actual current is the topological charge. So to be non-zero should allow a non-trivial field configuration that so the field is properly compact. And then once it is compact, then we know that is the compact boson is the same for a certain radius is the same as the fermion. So the fact that it has an anomaly is kind of obvious.
Yeah, that's a very good comment.
If you then try to solve this conservation law in terms of not of the boson, but you replace the boson with the bilinear of the fermion, you discover that in presence of the gauge field, you have to regularize by point splitting, and this point splitting will produce you the extra term that you put by hand.
Yeah.
But if I work this in the bosonic, in the compactified boson, it comes automatically. I don't have to do anything. It is known.
This, I definitely do not claim that this is not known. This is like
Okay.
in textbooks.
I mean,
Sorry.
what I want
Sorry
to
if I
say
gave
that,
you this impression.
no, I mean that is not, the example is not surprising in the sense that
What I'm saying is that this hydrodynamics of ideal fluid, this barotropic particular fluid, is some sort of bosonization of massless Dirac fermion.
Okay.
But it has also some degrees of freedom, which additional or maybe that you can reorganize them to get really massless Dirac and nothing else. I don't think it's nothing else. It's very interacting, very complicated dynamics, right?
in 3+1.
See, I'm talking 3+1 fluid
Okay.
is a complicated story, right? So, but there is some sector of it which looks like it can be imitated by massless Dirac.
Okay.
So you might have some massless Dirac plus some other things, and in some effective field theory approach, it reduces to Euler fluid. Maybe, but we start from Euler fluid, and indeed many things say that this theta field, or actually analogs of close relatives of that theta field are compact, should be compact. And in particular, I avoided here important thing, which is actually now current thing I'm trying to think about is that, and Paul Wigman understands all of that, but I did not yet, that's why I didn't talk about it. But in principle, you can consider only one pair of Clebsch's, because three-dimensional velocity field can be written in terms of just three Clebsch's.
Mhm.
Then the conservation of helicity is just topological like this, because the helicity in this case is just d theta, d alpha, d beta. If you integrate it also full space, and if boundary conditions are good, it's just full derivative 0. So this is much closer example to this one.
Mhm.
But the problem is that the symmetry origin of this, the same as symmetry origin of this, is not immediately clear. You have to expand. You have to either introduce dual fields there, or as I did, introduce several pairs here. That's why I did several pairs. But if you do it only with 3, then this theta, alpha, beta, beta and theta tend to be compact and want to form this singular vortices and all that.
Okay.
So it's a very
Thank
good
you.
comment.
Any other question? Okay, if not, let's thanks again.
Okay, thank you.